Hello everyone! Today we're going to look at the magnetic field from a wire, and we've already looked at that qualitatively, but we're going to use an equation today, and we're also going to look at the force between two current carrying wires. So here is our picture for the magnetic fields around a current carrying wire, and again, if we point our thumb in the direction of the current, then our fingers will curl around in the direction of these looping magnetic fields. So we've looked at that already. Now we're going to look at the magnitude of the magnetic field. We don't really have enough background to derive this at this point, but we're going to use it for some calculations. We will derive this later on. But it works out that it is this equation here where mu naught is a new constant that we're going to deal with. It is known as the permeability of free space. So we've already had the permittivity of free space, and now we have the permeability of free space. And it is defined as precisely 4 pi times 10 to the negative 7th. There is a negative sign there, so don't miss that. And we'll discuss later why this is a defined quantity as opposed to a measured quantity. And then you also have the magnetic field proportional to the current in the wire, inversely proportional to the distance from the wire, which we're calling r. So that would be the distance out this way is r. Okay. Now, qualitatively, real quickly, if we think about these wires producing magnetic fields, and we want to know which one of these is going to have the greatest magnetic field here right in the middle, our convention with these x's and dots is the x is going away from you or into the page, and the dot is coming toward you. So if you think about the magnetic fields, if you point your thumb toward yourself and curl your fingers, this guy is going to be making magnetic fields curling around in that direction. At the center, it's going to make a magnetic field this way. This guy is going to make it that way, and we can go ahead and draw all of those nice vectors. So these are the different vectors we'll get from the different wires. In this case, they will all cancel out, so you'll have 0 magnetic field right in the middle. These guys, the vertical components, will cancel out, but you will be left with a horizontal magnetic field right in the middle there. So this orientation here will give you a greater magnetic field because that's greater than 0, obviously. Alright, on to forces. If we have two wires next to each other, there will be a force between the two because one of these wires, well, they'll both be creating magnetic fields, but if we look at this from the perspective of one of the wires, and we'll look at it from the perspective of wire 2, that wire doesn't care about the magnetic field that itself is creating. It just cares about the magnetic field that wire 1 is creating. So it says, oh, there's a magnetic field here from that other wire. Now, it's a current carrying wire, and current carrying wires in magnetic fields feel forces. So if we first look at the magnitude of that magnetic field from wire 1, that's why we call it B1, because it's the field from wire 1. That is equal to this expression here, where the I is the current in wire 1. R, we're just going to call that D for the separation distance. Then I've got wire 2, and it's feeling a force from that magnetic field, and that force is equal to ILB sine theta. Now theta is the angle between the direction of your current and the magnetic field. And I should mention that this analysis is for perfectly parallel wires. So if you ever have perfectly parallel wires, regardless of how close they are, the current is always going to be perpendicular to the magnetic field because the magnetic field is going into the page at this location. The current is going straight up. So that means sine theta is going to be sine of 90, which is just going to be 1. So I just get ILB. Oh, and I should mention this is the force on wire 2, and that depends on the current in wire 2. So now I just need to plug in this for the magnetic field, and I get the force on wire 2 is I2 times L times mu naught I1 all over 2 pi times the separation distance. If I rearrange this and write it in prettier writing, I end up with this expression here. So we find that the force is proportional to the current in each wire, the separation distance, and then the lengths of each wire. A lot of times we divide both sides by length so that we just get force per unit length, something like this, where it goes away. Alright, so that's about it. We've got our nice expression here, and this is what most of your calculations are going to be using. We also need to think about the direction of this force, though. If we think about up here, this expression here, ILB, that actually came from IL cross B, and if you remember, we put our fingers in the direction of the current, point our palm down or into the page, then our thumb will be pointing in the direction of the force. So this guy will be feeling a force in that direction, so there will be an attractive force. And you can reverse all of this analysis and say, well, wire 1 doesn't feel its own field, it says that wire 2 is producing a field, and you'd essentially just switch your 1s and 2s and you'd get the exact same result. And by Newton's third law, we know that they both have to feel the force as well in opposite directions. So essentially we can say that if the currents are both in the same direction, they will both feel an attractive force. And you might have guessed it, if we have currents in opposite directions, essentially these fields are the same here, right? But now we've got our fingers pointing down and then our palm pointing into the page, so now our thumb is going to be pointing to the right. So opposites in this case do not attract. If they are currents in parallel wires, opposite currents repel, whereas currents in the same direction attract. All right, that's it. Thanks.